Okay. Assalamualaikum warahmatullahi wabarakatuh. Very good morning, everyone. So thank you for joining this session. So today we are in week 5 already. So just housekeeping for today, just to recap or just to look forward what we're going to cover for this course. So we had our first tutorial in week 4. And then we had our first lab, Marset Boiler, this week. So thank you for students who attended the 2 sessions. And for these 2 weeks, week 5 and week 6, for next week, we are going to cover Rankine cycle, and hopefully we can finish everything by next Friday. And then on week 7, just a friendly reminder, we will be having our first test scheduled on the 30th of November 2021. This is on Tuesday at night. Okay, so please be aware. And then we are also going to have your assignment. The first assignment will be due on the 2nd of December. And then on the Friday before the midterm break, we are going to have the industrial talk scheduled during the class session. Okay, so please be reminded that the test obviously is compulsory as well as the industrial talk. So please make sure you attend the talk. And I intend to give bonus points for students who ask questions during the talk. And also I plan to conduct a quiz based on the topics covered during the talk in the next meeting. Okay, all right. So basically, after week 7, and then you'll be off for your midterm break, and then we will continue with week 8. And starting from week 8 onwards, Dr. Nama will take over, and we'll continue with CO2 and also CO3. Okay, so I hope everyone is aware of this plan. And if you got any questions, please let me know. Okay, so if there are none, so let's continue with today's lesson. All right, so for today, we will start with a new chapter in your textbook. It should be chapter 10, which is the vapor and combined power cycles. So the objectives for this chapter or for this topic are listed as follows. So we'll analyze the vapor power cycles in which the working fluid is alternately vaporized and condensed. So if you remember from the first one that we learned for gas power cycle, where we examine, we investigate, we look at the 3 main cycles, which are Otto, diesels, and also Rankine. They use the ideal gas, basically, where the substance or the properties of the gas do not change phase. Okay, but right now, for this chapter, we will be looking at the phase change, or how the substance change from one phase to another in a system. Okay, so that's why it says here alternately vaporized and condensed. So meaning that vaporized is vapor, obviously steam, and condensed is in terms of liquid. And then we look at or we study on ways to modify the basic Rankine vapor power cycle to increase the cycle thermal efficiency. So basically, again, we will be looking at the idealized Rankine cycle, which we are going to cover a bit. And basically, we can look at from the basic and then how we can improve the basic Rankine cycle based on a few methods. Next, we will look at ways to analyze the reheat and regenerative vapor power cycles. So basically, apart from the basic one, we will look at several modifications that can be made for the cycles. Okay, then we'll perform the second law analysis of vapor power cycles, and then look at a process called cogeneration. And finally, we'll just briefly discuss a system or power cycles that consists of 2 separate cycles, okay, which is called combined. Okay, so that's the end of the chapter. All right. So as for the introduction, so just to summarize, the term vapor power cycle implies that the working fluid is alternatively vaporized and condensed during the cycle. So this is what I meant by phase change. So it involves phase change. Okay? So these gases phase typically exist near the saturated vapor line. So these cycles, basically, now we will be using the TS diagram, and also if you remember back in Term 1, the saturated vapor line, the liquid line, the mixture region, we will be using that a lot to analyze the cycle. Okay? And a second point, steam or water is the most common working fluid used in vapor power cycles. It is cheap, easily available, non-toxic, and has a high enthalpy of vaporization. About this point, we will discuss a bit detail at the end. Basically, actually why, even though we analyze in Rankine cycle, the substance that we use in analyzing idealized cycle is steam and water, the substance, but hopefully we will cover at the end of this topic, we will discuss how actually steam or water is not the best substance to be used actually. There are other substances that we are going to compare and discuss in comparative to the water as the main substance in the cycles. Okay? And then finally, the last point, most vapor power plants are steam power plants, whether powered by coal, natural gas, or nuclear. So we'll discuss a bit about several types of power plants, and this actually can contribute, or you can use some of this point for your assignment. Okay, so we'll touch on that in a bit. All right, so the first example, or the easiest example to give you some idea of how this cycle works, okay, or the use of the cycle is in terms of steam locomotive. Okay, as you all know, right now steam locomotive no longer used commercially. It has been phased out. If you see one probably from Harry Potter, for example, the one on the bottom right here is from Harry Potter. So they use it for leisure, for exhibition, not for commercial or basically for the main main mode of transportation anymore. Okay, but the steam locomotive basically utilize the concept of Rankine cycle. So we are going to have a look at one video that give some explanation of how the steam locomotive works, basically using the vapor cycles. Okay, so let's have a look. Okay. All right, so I hope you can hear the sound coming from this video. So if you can't hear anything, please let me know. So I'm playing now. Sure, my computer does not support this format. Okay. All right. So what I will do is I'm going to stop sharing for a bit.
Work. Invention of the commercial steam engine, starting the Industrial Revolution, these icons of progress made travel and transportation by rail a viable option, cutting travel times and connecting communities. Here's a somewhat simplified steam locomotive. Many trains of this era, the boiler
Okay, so basically I was asking in the chat box, so can you guys hear the sound or explanation? No, no sound. Okay. Just give me 1 second and let me try again using my microphone, and please let me know whether you can hear it or not. Okay. Okay, one more time. To start playing.
Invention of the commercial steam engine, starting the Industrial Revolution.
Okay, how about now?
These icons of progress made travel and transportation a viable option, cutting travel times and connecting communities. Here's a somewhat simplified steam locomotive. With many trains of this era, the boiler is clearly distinguishable. A steam locomotive needs water and fuel, usually coal, carrying them either on the locomotive itself or in a tender pulled behind. The fuel is used to run a fire inside the engine, burning inside what's called the firebox. The fire is managed by the fireman in the cab, who, along with the driver, is needed to run the steam locomotive. The firebox sucks air from underneath the train to keep the fire from starving. The solid fuel sits on top of grates, through which dead ash can fall down into the ash pan. The firebox allows heat and smoke to escape the chamber through the so-called fire tubes, running the length of the boiler. The boiler wraps around the firebox and fire tubes, thus heating the water inside to boiling point, creating steam. As more and more water evaporates, steam builds up inside the boiler, creating pressure. Inside the steam dome, the steam can find a way out of the boiler towards the cylinders. In case the pressure becomes too high and the boiler risks exploding, a safety valve pops to relieve pressure. The amount of steam exiting the boiler is controlled using the regulator valve. This is effectively the throttle of the steam locomotive, because as the steam runs down to the cylinders, we get to the part that actually drives the wheels. There are two sets of cylinders, one set on each side of the train. Steam engines on steam locomotives are so-called reciprocating piston engines. Each set has one cylinder with a piston, connected to the driving rod, which in turn is connected to the driving wheel, which can be connected to the other wheels. The other cylinder contains the slide valve, which allows fresh steam to enter and used steam to exhaust from the piston cylinder. This way, the piston is pushed once from both sides to complete one rotation, creating that reciprocating motion, which is then used to rotate the drive wheel. The steam, now done with its job, exits towards the smoke box, where it joins any smoke coming off the firebox to escape out the chimney. If you want, for instance, a more in-depth look into trains, let me know in the comments below. Subscribe and hit that.
Okay, so that's all about the video. So, okay, so hopefully you all get some idea just now on how the steam locomotive works. So basically that's pretty much what we are going to learn today. But obviously steam locomotive is a very not simple, but do not possess the components that we are going to look today. For example, the condenser, boiler, and turbine. But the concept is very similar, where you have a substance, in this case water, and you heat up the water until the phase change from liquid into vapor, and then that vapor basically now in terms of a very high pressure is now being used to do work. All right, so just think for a moment. Back in those days, maybe 1800 or 1900s, in that year, those train, basically the locomotives, trains, they are very, very heavy, made from solid metal. And can you just imagine the pressure involved to drive those trains? Okay, not just the train, but along with cargo as well as the passengers. Okay? So that's why we need to take some time to appreciate those engineering innovation, even though this is back in 200-300 years ago. Okay, they already can come up with a solution to make their life easy. Okay, so just again think about that and relate to what we just learned in our first lab. So in Marset boiler, okay, obviously the pressure involved is not as high as this, but I think about 2 or 3 groups during the lab session. At the end of the session, Encik Nizam, he basically opened the relief valve to let out the pressure right after the lab concluded. Okay? And remember, at the end of the lab, the pressure, I think, was about maybe 10 or maybe 10.5, about 10 to 11 bar. Okay? And the pressure, the corresponding pressure, I think was about 180 to 190, roughly about that. Okay? So just imagine, in that small tank, we can generate a pressure of up about 10 bar. And 10 bar, if you remember, is 10 times the atmospheric pressure. So that amount of energy or that amount of pressure, when we release that, you can hear the sound and you can see like the vapor or the smoke coming out from the tank. Okay, and now just imagine, from this small Marset boiler equipment, instead of that dimension, now we have a full dimension of the train that basically is being used to heat up the water. Okay, so just imagine the tremendous pressure involved. Okay. All right, so let's continue with our lesson. Okay. As usual, before we proceed into the idealized cycle that we want to learn, so let's have an understanding of the Cardinal vapor cycle. Okay. So as everyone understands, the Cardinal cycle is the idealized cycle for all types of applications, basically, in order to understand the limit here, the maximum limit or the maximum efficiency that can be extracted from that particular cycle. Okay, so when we look at this Cardinal vapor cycle, the corresponding TS diagram is given here. Okay, so the processes are as follows. Okay, so 1 to 2 is the isothermal heat addition in the boiler. So 1 to 2 is isothermal heat addition. So Q in, okay, that's a boiler. 2 to 3, isentropic expansion in a turbine. So basically, when we have turbine, meaning that we have W out. Okay, 2 to 3. And then 3 to 4, isothermal heat rejection in the condenser. So now we have Q out at the condenser. And then finally, 4 to 1, isentropic compression in the compressor. So basically, over here, we need W in. So that's roughly about Cardinal vapor cycle. So some notes over here. We understand that Cardinal cycle is the most efficient cycle. Yeah, I'm going to highlight here. The most efficient cycle, operating between 2 specified temperature limits, but it is not suitable. Okay, so the keywords here: the most efficient, but it is not suitable model. Okay, for a few reasons. Okay. So why Carnot cycle is something that we can learn, something that can be used to get the most efficiency. For example, if you want to know the limit of our cycle, we can use this. But in real life, it's not possible for 3 reasons. Okay, for example, for process 1, okay, for process 1 to 2, basically we are limiting the heat transfer processes to 2-phase system severely limits the maximum temperature. So if you see over here, 1 to 2 is here, which is the boiler. Okay, so basically we limit our heat transfer process. Okay, and basically for this particular region or this particular cycles, we can get up until 374 degrees Celsius. Okay, so that's the limit. Okay, so when we limit the temperature that can be used, meaning that the output that can be extracted will also be less. So that's the first one. Secondly, process 2 to 3. Okay, 2 to 3 is basically the turbine here. The turbines cannot handle steam with a high moisture content because of the impingement of liquid droplets on the turbine blades, causing erosion and wear. Okay, now, this relates to what we have learned in Thermo 1. Okay, if you look at over here, so I'm going to label again, 1, 2, 3 over here. So remember, this is W out, this is turbine. So what happened is when we have a high steam from exiting the boiler and getting into the turbine. So this high steam will basically, steam or vapor will basically do the work by rotating or using the kinetic energy, rotating the turbine, the blades in the turbine, hence generating work, okay, W out. So after some work is being done, so basically the vapor or the steam will lose some power. So because it loses some kinetic energy, okay? So some energy is being lost. So the loss of energy of the energy can be translated by the drop in temperature over here. So from 2 to 3. So there is a drop in temperature. Okay. So if you notice over here, the location where the exit of the turbine at point 3. So if I draw a turbine over here, a symbol of the turbine. So let's say this is 2 and this is 3, state 3. Okay. So when the steam exited the turbine at this particular location, and if you relate back to Thermo 1, what is this in between the dome? It is the saturated mixture region. Okay, liquid region. It's not liquid region, sorry, liquid on the left. So it's a mixture region. Okay, so and we learned that in terms of the diagram. Okay, as we go to the left, this is purely liquid, and if we go to the right, this is purely vapor. Okay, and in between here, what we have is the mixture, obviously. Okay, as we move closer to the right, okay, basically we have more vapor compared to liquid. Okay, if you look over here at point 3, where the location of the turbine exits, it is quite far inside, meaning that there will be a lot of droplets exiting the turbine. And this droplet basically is not desirable because it will cause high moisture content, hence causing the erosion and wear. Okay, so that's something that we want to avoid. Okay, later on, when we look at in detail of how this diagram works, we will see that our target or the desirable location is very, very close to the this region, very, very close to the vapor region or saturated vapor line. Okay, so that's what we are going to look later. And finally, the second phase, the third point, it's not practical to design a compressor that handles 2 phases. Okay, so if you look over here, from 4 to 1, this is compressor. And the purpose of a compressor is basically to compress liquid. Liquid basically is just pure liquid, not, for example, we know that in this region, this is basically liquid plus vapor, hence 2 phases. So we do not want that. Okay? And later on, when we look at the ideal Rankine cycle, we want our compressor to be located on the left region, okay, outside of the dome. So these are the limitations of the Cardinal cycle that basically can be used to understand the maximum efficiency available for our system, but is limited for these 3 particular reasons. Okay, so let's get to know Rankine cycle or the ideal cycle for vapor power cycle. Okay. All right, so So many of the impracticalities associated with the Cardinal cycle can be eliminated by using these two processes. First, by superheating the steam in the boiler, and secondly, by condensing it completely in the condenser. So let's look at the components involved first. Okay, the components here. First, from 1 to 2, we have pump. And then from 2 to 3, we have boiler. And this boiler is now being represented by Q in. For pump, is being represented by W pump in. And then from 3 to 4, that's basically the turbine. Okay, we have W out over here, W turbine out. And finally, 4 to 1, we have Q out, which is the condenser. And this diagram is very, very useful because it gives some idea of the temperature involved, okay, especially here. When you see over here from 2, okay, so when the liquid enters the boiler, it's still in blue region. Okay, means that it's quite cold. So once it enters the boiler, obviously Q in, so heat is being added, okay, the substance is being heated. Then what comes out is basically in dark red, meaning that it is liquid at a high temperature. Then after the liquid enters the turbine, some work is being done. Remember, the steam is being used to rotate the turbine. And then when some of the steam or some basically when the substance exits the turbine, okay, at stage 4, some of the energy already lost because of the work being done. Hence, if you see over here, the color region at stage 4 is light red, meaning that the temperature associated at this particular stage is less than 3. So T4 is less than T3. So let's look at in terms of the TS diagram, okay, how this process can be translated. So from 1 to 2, if you look over here, yeah, I'm going to zoom in. Okay, so 1 to 2 is the W pump in. Okay, remember you need to draw or need to label W pump in to make your diagram complete. So that's the compressor. And if you notice, compared to the Cardinal cycle just now, instead of in between here under the dome, we now have our compressor located outside the dome, which is in the liquid region. So liquid region. So the compressor basically just compresses the liquid, okay, from 1 to 2. And from 2 to 3, this is Q in. So this is the boiler basically. Okay, heat is being added, and at a constant pressure, if you look over here, this line represents the constant pressure line. Okay, so heat is being added to the liquid. Okay, so the temperature rises at constant pressure up until 0.3, and over here we all know this is a superheated region. Okay, so at 0.3, then this is heater. Then after 0.3, the steam now enters the turbine, work is being done, so we have W turbine out. Okay, and because work is being done, the substance loses kinetic energy, so there is a drop in temperature up until stage 4. And if you look over here, stage 4, the location or the exit of the turbine, the most desirable location is to be very, very close to the vapor line. Okay, remember, this is vapor line. Okay. And if you remember from trouble 1, in terms of the quality, we know X quality, okay, is between 0 and 1, and 0 is 100% liquid, 1 is 100% vapor. So just to label on the diagram, let's use this color. So this is 0, and this line is 1. Okay, in reality, we can't get close. It's not get close. We can't get exactly on 1. So, but we want our quality or the X value to be roughly about 0.85 to 0.9. Okay, meaning that we have less moisture in the system to avoid basically damaging the blades. All right. And then finally, 4 to 1 is Q out for the condenser. Okay. So that's the ideal Rankine cycle. And okay, the ideal Rankine cycle does not involve any internal irreversibility. Okay. Again, if you remember, this is ideal. It's not possible to be achieved in real life. Okay, but for the sake of understanding, analyzing the cycle, we make several assumptions. Among them is that it doesn't involve any irreversibility. Okay, all right. Okay, as for the processes, okay, it's highlighted over here. Okay, from 1 to 2, isentropic compression in a pump. Okay, 1 to 2, and then we have constant pressure heat addition in the boiler, which we can see from this line over here, constant pressure heat addition. Next is isentropic expansion in the turbine. Okay, and finally constant pressure heat rejection. Constant pressure because of it follows the line over here. So that are the processes for the ideal Rankine cycle. If you got any questions, please you can ask question or put your question in the chat box. All right. Okay. So again, this is similar to what we just covered. Basically, just a little bit of explanation of what is happening basically. Okay. Okay, I give you about 1 or 2 minutes just to look at this diagram and understand the working principle of it, and then we'll proceed from here. Okay, I think the takeaway from this diagram is that you first need to understand how this ideal Rankine cycle differs from the Cardinal cycle for the vapor cycles. That's one thing, especially for example here. Okay, I emphasize over there just now for Cardinal cycle we have a two-phase compression system, which doesn't make any sense. But right now we are just focusing on compressing the liquid, okay, because from here to from 1 to 2 is 100% liquid. Okay, and for process 2 to 3, okay, so for the boiler process, we now is being replaced by a process of Q in. Okay, so it follows this line 2 to 3 at the constant pressure process. Okay, all right, and finally for turbine and condenser, it's pretty much the same that like we discussed. It's important to have the quality or to remove as much droplets as possible to avoid wear and erosion. Okay. Okay. And of course, it's also important for us to understand some of the energy equations that relates to the ideal Rankine cycle. Okay. So the first one, if we look at the system, we can proceed with the steady flow energy equations. Okay, and we start with Q minus W equals to delta E, and delta E basically equals to delta U plus, if you look over here, we can cross out delta KE and PE because the kinetic energy influence is very, very minimal, so we can cross it out. And also potential energy is very, very minimal because it doesn't involve change in height that much. Okay. Okay, from here, we can expand our equations to be Q in, Q out plus W in, W out. So just I want to emphasize over here. Okay, I make some notes over here. Unit convention. Okay. Again, this brings back from Thermo 1, what is positive W in, what is positive W out, or what is positive Q in, what is positive Q out. It's very, very important to know the sign convention. Q in positive, Q out negative for work. W in is positive, work being done by the system is negative. So we have to understand that. Okay. So from here, this delta U, okay, basically can be equated to enthalpy exit minus enthalpy I. Okay. And then for pump, okay, this is important because we will be using this a lot. Okay. For pump, we can calculate the work involved using two steps or two equations. First, by using the enthalpy, okay, because it involves a liquid. So W pump in equals to H2 minus H1. And W pump in can also be calculated by using the following equation, which is VPU minus P1, okay, pressure and volume. So this is very important because we will be using this in our calculation. Okay. And it's important to note over here, if you look at the diagram here, the point 1, the location of point 1 basically is on the saturated liquid line. And from Thermo 1, back when we learned about the property tables, we can get the properties of H1 or the location when we have something on along the saturated liquid line to be HF or at P1. Basically, we can get the enthalpy of the liquid at this particular pressure. Okay. Similarly, if you want to calculate the specific volume or to find the specific volume for 1, we can get the value at P1 by using P1. Okay. All right. Next, for the boiler. For the boiler, there is no work being done, so we can get Q in equals to H3 minus H2. For the turbine, there is no heat needed, so Q equals to 0. So we can get W turbine out equals to H3 minus H4. And finally, for condenser, okay, there is no work being done, so we can get Q out H4 minus H1. So all these basically are the equations, the summary of equations that will be used to solve problems related to ideal Rankine cycle. Okay. And finally, as always, we are required to find, or we want to find, the efficiency of our cycle. So we can use W net equals to Q in minus Q out, or W turbine out equals minus W pump in. Okay. Always remember, you can use these two. Okay. Q in, Q out, or turbine out, pump in. Okay. And the efficiency, okay, similar with other processes, is W net divided by Q in. Basically, what can be produced divided by what is being input, or what is being basically the energy being given to the system. So W net divided by Q in, which is can be summarized as the following: 1 minus Q out divided by Q in. Okay. So these are the energy or the efficiency equations that will be used similar to other processes. Okay. So we look at this diagram. Okay. Let's take a 5-minute break, and then we will continue roughly about 11:05 with basically we look at specific components and how they work. All right. So let's take a 5-minute break, and then we'll continue in a bit. Thank you. Okay. So let's proceed to look at the components that basically made up this Rankine cycle. Eh? All right. First, we look at the boiler. If you look at the diagram, okay, I think the diagram basically doesn't do any justice because we just look at this particular component that is stated as boiler, and then we just have look at we have a Q in going into the boiler. Okay, but if you look in detail, okay, what makes a boiler a boiler? So it's not just as a simple box, and then we put fuel plus air, and then we get fire, for example, and heat up the substance. So it's actually more complicated than that. And if you look over here, this is basically a simplified or the simplified working principle for general boiler. Okay, so for example, if you look over here, we have air. Okay, basically air here goes into this channel or this piping. Okay, and along this pipe, okay, we have this fin. Okay? And if you remember, fin basically acts as a heat exchanger. There basically we want basically, even though we want to increase the surface area, because fin, the purpose of the fin is to increase the surface area of any particular component that we want to increase the heat transfer. But from heat transfer cost, if you remember, there is a limit, or there is an optimal design and numbers where or how many fins can be added to a particular system. So it's just not like we add, for example, 100 fins, the efficiency or the heat transfer will increase. Okay, there is a calculation to find out the optimal heat transfer or the optimal fin numbers. Okay, so as you can see, so we have fins. Okay, then the air is now passed through a blower, and now is being blown into the system. Okay, of course we have a burner. Okay, now air is now being heated. Okay, so this basically come out as Q radiation, so heat due to radiation. Okay, so due to this radiation, okay, and if you look over here, this is the water from the pump. Okay, if you remember, 1 to 2 is from the pump. Okay, so this is basically start from 2, because 2 to 3 is the boiler. So water from the pump, okay, now passes through here, and again we have fin over here to increase the surface area so that the heat transfer can be increased. It passes through this, and you can see over here, it passes through this boiler, okay, where the heat is being absorbed by the pipe, okay, in terms of the Q radiation. Okay, now from liquid, okay, maybe this is liquid, so it's being heated up. Okay, by the time it exits here, they should be in terms of the vapor already. Okay, so in terms of superheated steam, it again not finished yet. We go back and then again pass through the system again, so that we can increase the temperature of the substance before it enters the turbine at point 3. So this is just to give you some idea of how a boiler works. All right, so hopefully we appreciate the technology, or we appreciate the working principle of something that helps us produce goods. And for example, if for the Western countries in the winter, okay, they require heat from the heat pump, for example. So it's not as simple as aircon, for example. It's we just know we want something, the room to be cool. Okay, but we don't know what is happening behind that. So that's why it's important to understand what is happening so that we can improve the system, okay, once we start working. All right. So again, to give you some perspective, if you look over here, this is the standard size of the equipments that we generally deal in the industry. Okay, so it's not just as small as the Marset boiler that we did for the first experiment. So this is the scale involved in the industry. Okay. And for example, again, you can see here, and again, right, the size or the scale of the equipments. Okay. And I think this is quite relevant. So this is an example of the turbine. Okay. So these obviously, these are the blades. Okay. And you can see like the scale or the size of the blade is huge. Okay? And you can just see here the bolt and nuts over here. Okay? So this basically is capable, okay, because when the steam enters the turbine, okay, and the blade is being rotated because of the steam, the high kinetic energy from the steam keep on pushing the blades. So we have W out over here, okay, and obviously we want the maximum W out possible, hence the scale of this turbine. Okay, so not necessarily bigger turbine, bigger output, but just we look from this turbine, basically we can expect the output to be ginormous. Okay? All right. So again, to relate again what we are learning and what is being used in industry, as well as relate or to answer the assignment questions. Okay, because in the assignment question you need to choose one example of real life applications. Okay, and I would like to remind, please, to not just copy and paste everything. Okay, make sure you understand the cycles that you use or the applications that you use, and try to explain it and relate to what you are learning in the class. Okay. So, for example, this is the design of a nuclear power plant with a pressurized water reactor. Okay. I think we talked a bit about this previously at the start of the semester. So maybe I'm not going to go through here. Okay, but what we can relate is, okay, there are two things. First, the one that is circled here, number 8. So in this system, we have two sets of turbines. Okay, let's say this is turbine A and turbine B. And later on, when we look into details, okay, and if we can relate with the Brighton cycle, this usually, the first one is called high pressure turbine. Okay? And the second one is called low pressure turbine, okay, which we are going to discuss in a bit, okay, why they are called low pressure turbine or high pressure turbines. Okay? So this turbine, basically, they get the heat or the heat basically that rotates the blade comes from the reactor here. So this is the nuclear reactor, number 7, fuel element. So it heats up the substance. In this case, it can be liquid, because this is usually a reservoir. Can be, for example, can be a large river, or it can be ocean. For example, the Fukushima Daiichi. Okay. So this water is being heated up, and then the steam goes into the system, okay, rotating the blades. Okay, and then we have a second system rotating the second blade, and then producing, basically rotating the generator to produce electricity. So that's pretty much the concept of the Rankine cycle. And obviously, if you look over here, we have a condenser, okay, because after work is being done on the system, okay, the blades, and then it goes out here, down here, and then it needs to be cooled, okay, because the process needs to be repeated. So to cool the water, because remember, the water that passed through the blades are still at very high temperature. So to do that, they use this number 15. This is basically the cooling tower. Okay? Cooling tower, basically to reduce or to remove the temperature into the environment. Okay? And then the cycle will proceed again with, this is pump, okay, condenser, pump. This is kind of like a heater, anything that gives Q in. Okay? And then of course blades. So that's the general working principle of a Rankine cycle. So this is for nuclear power plants. So similarly, what we have there in nuclear power plant is quite similar to what we have for the coal-fired steam power plant. Okay, so again, the concept is quite similar. So you can see that we have boiler over here, and you can see that the piping actually is not just straight. Okay, piping similar to the one in we're not what we are going to cover in refrigeration cycle. If you notice, as I said before, behind or under your fridge, you'll see that the coil. Okay, the coil is not just a straight coil. Okay, basically they arrange it to maximize the surface area. So similar to what you are looking over here, they want to maximize the surface area, to increase the surface area. So they have coil like this, okay, where they arrange to get the maximum values that they want. All right. Okay, so now we understand a bit about Rankine power cycle, and we can see that they are used in the industry, for example, for coal power plant to produce electricity. Okay, so that's the general idea of it. Okay. Now, as part of our course, we also need to understand something that is been going on for a couple of years now, which is called the SDG. SDG stands for Sustainable Development Goals. This is a very, very important concept. Okay, basically it comes from the United Nations. There are 70 goals to transform our goal. Okay, basically, if you look over here, this agenda, they call it the agenda, basically requires all nations, okay, regardless whether developing nations or poor or nations, we all need to come up with our set or our goal to address this 17 agenda. Okay, so in our case, for example, in our syllabus, the most relevant agenda for Turbo 2 probably is number 7, which is affordable and clean energy, and as well as number 13, which is the climate change. Okay. And why am I telling you this? Why we are discussing about this? Okay, first, SDG is not just for academic. It involves the government, it involves industry. So basically, everyone needs to come up with a solution, to propose a solution, and need to address the specific areas that is listed over here, the 17 areas. Okay, we talk about this in a bit. Okay, so basically, all nations, including Malaysia, has made set of targets and also policies in order for us to achieve whatever target that we set in these 17 agendas. Okay, so let's have a look in detail. Okay, so if you look for number 7, which I think we can relate to Turbo 2, which is affordable and clean energy. Okay, so basically this goal, this agenda, basically the aim is to ensure access to affordable, reliable, sustainable, and modern energy for all. Okay, the reason is simple. Okay, it's given in this info diagram. So the first one, 1/3 of the world's population use dangerous and inefficient cooking system. Okay, that's the first issues. Okay. 1/3 means 2.6 billion, by the way. Okay, and then we still have about 700 million plus people lack access to electricity. Okay, and majority of them live in the sub-Saharan Africa, so Africa region. Okay. And then the next issue is about the energy efficiency improvement rate needs acceleration. Okay, and finally, the accelerated action on modern renewable energy is needed. So this is what we want to touch basically. If you notice what we are discussing right now, and actually for Thermodynamics 2, we are discussing the industrial application of the cycle using fuel, which is something that could be rendered obsolete in the next 50 or 100 years. We are still learning about this because this is still the mature technology. We are still using this on the road, for example, or even in industry. But moving forward, this is the critical area, which is renewable energy. Okay, well, I'll explain in a bit why the modern renewable energy is the concept that everyone needs to understand and play part. Okay, right. So in Malaysia, the SDG is being handled under the EPU, Economic Planning Units. Okay, currently the minister responsible for this is Datuk Sri Mustafa Muhammad. So it's good in a way that we have this EPU unit, which is a very, very high-profile unit under the Prime Minister's office that oversees the achievement or the target sets for achieving this SDG. Okay. So we have some introduction over here. I will share this website for you to have a look at, which I think is quite interesting to see where we are right now and how we can achieve the set target by Malaysia. All right. Okay. Okay. So for Malaysia, basically, the good thing is that we have mapped or we have tried to address all the 17th agenda by basically it's not just separating, but organizing them into a different categories, and more importantly, it has been mapped to the 11th Malaysian Plan and also 12th Malaysian Plan that is currently being discussed in the Parliament. Okay. So at least we are doing something about it. Okay. So if you see over here, the 12th Malaysian Plan is highlighted over here. Okay. So we are doing something to address this issue. Okay. So this, I think, is from the review of the SDG achievement from the website. Okay. I'm not going to focus everything. I'm just going to focus here. Goal number 7. Here. So if you look over here, goal number 7, affordable and clean energy. If you look over here, the summary state that we have almost 100% population with access to electricity in 2016 and 19. This obviously is good. Almost all of our population have access to electricity, but what it doesn't say is how we are going to use renewable energy into improving the livelihood of the nation and the people. How we can reduce dependency on the hydrocarbons from oil, basically. So, but it didn't address that. So, from my perspective, it seems that we have a very, very long way to go in order for us to achieve the SDG target. Okay? Even though we are getting there, we have planned, okay? But I will explain in a bit why I think we need to do more. Okay? And by when I say we, it means it affects me as a researcher, you as a student, which you are going to graduate soon, will become an engineer, and this issue will not just stop at you, your generation. It will stop at the next generation, which is your child, and probably the next generation after that, which is your grandchild. So it's very, very important to understand that this is not something that you say, oh, this is okay. This is not my problem for now. Just leave it to the adults. I'll take care of it in 20, 30 years time. No. Most of the activities right now, if you notice, whenever we have a climate conference, most of the activities are very, very young. Okay, so it doesn't matter the age actually. Okay, and these issues basically definitely needs to be addressed by all generations. Okay, let's have a look. Okay, if you read the news for the past 2 or 3 weeks, you should notice most of the topics are related to this COP26. So COP26 just concluded last week. It's about the climate change conference. Okay, all the key players, key government agencies, basically sit down together to come up with a solution to address the climate change. Okay. And again, I would like to relate why we are talking about climate change in our class. Remember, we talk about gas power cycle, and we talk about the vapor power cycle. And this is Otto, this is diesel, and then we have Brighton, and right now Rankine. Do you notice the similarity between all the cycles? They produce emission, okay, or may I add, harmful emission. So this emission or greenhouse gases basically contribute to climate change. Okay. So this conference basically try to get everyone together to commit. Okay, and if you notice, and if you read, if you're into renewable energy or you understand what is happening nowadays, the target set by UN is for the global warming, the increase of temperature in the global warming, to be limited to just 1.5 degrees Celsius for the next 100 years. Because if we keep on the track that we are right now, meaning that pollution is uncontrollable, we do not move from conventional energy, which is hydrocarbons, fuel, and then we do not move into renewable energy, for the next 100 years, we will have an increase of temperature between 2.5 to 3 degrees Celsius. It may not seem a lot. You might say, it's normal to get 32, 35. That's 35 degrees standard. Okay. But if we have an increase from the normal temperature by 1 degree Celsius, it will have an influence, a huge influence on the livelihood of everyone. If you increase by 2 to 3 degrees Celsius, it will be catastrophic to the world. Means the world that we're living right now. And this must happen, or this must be controlled within the next 50 to 100 years. So their target is so that by 2050, the world basically produce net zero carbon, meaning that by 2050, basically all the countries in the world no longer producing carbon emission, meaning that everything is switched on from, we switch from the conventional fuel. For example, instead of petrol car, diesel car, we now move into using electric car. So that's the aim, in net zero carbon by 2050. Okay, so it's very, very interesting. But again, as I said, it's not about my generation or someone's generation. It's about all of us. Okay, so that's why you need to know, you need to understand, so that hopefully by the time you graduate, you go into the industry, you are more interested into renewable energy and try to basically reduce the emission caused by the industrial applications. Okay, so hopefully. All right. Okay, so let's continue. If you got any questions about COP26 or what we just discussed, just please let me know. Okay. All right. So again, as in Brighton, what we are learning right now is idealized cycle, but we can't expect the cycle to be 100% the same, okay? Because we expect some deviation, okay, due to the reversibility, okay? Irreversibility. Okay, so let's have a look. Okay, so what are the causes or the influence that cause our deviations from the idealized cycle? Okay, so some of the efficiency encountered in the actual vapor power cycle with superheating, okay, are listed as follows. Okay, so the first one, the pump requires greater W in, okay, hence achieving a higher entropy at state 2A due to pump irreversibility. Okay, so for example, you zoom out over here. So the first one is the irreversibility due to the pump. Okay, we cannot get from 1 to 2 a straight entropy or higher entropy. Okay, there is some deviation caused by the irreversibility in the pump. And secondly, pressure drop due to friction in the boiler and pipes. So this basically, if I can highlight this region, this is due to the irreversibility or the pressure drop in the boiler. And finally, the irreversibility due to the pump. So that's the reason why we expect, or the reason why something that we learn in the idealized cycle cannot be replicated in the real life, okay? Due to the pump, pressure in the boiler, and the turbine. Okay. All right. So let's look at how we can increase the efficiency of the Rankine cycle. Okay. So the idea is very, very simple. To summarize, we can increase the efficiency by increasing the area under the graph or the plot. Okay, so let's have a look. Okay, here, the first one, increase the average temperature at which the heat is transferred to the working fluid in the boiler. So, meaning that we want to increase the area here, the area for the boiler, under the boiler. Second, we decrease the average temperature at which heat is rejected from the condenser. So here. So instead of here, we want our lines to be here. Okay. Again, remember, increasing the area under the curve basically reflects to the higher efficiency. Okay. So let's look at the first one. Okay, so the first one is by lowering the condenser pressure. Okay, when we lower the T flow average. Okay, so let's look at the points. This will increase the heat rejection and increase network. Okay, because if you look over here, point 4 is the original position. 4 prime and 1 prime is what happened when we decrease or lower the pressure. Okay, we pull down the lines. Okay, 4 prime and 1 prime refers to the new lines. Okay, if we lower down the pressure. Okay, when we lower down the pressure, okay, what you'll have is here. Okay, as noted by the notes here, which is the increase in W net, because we have an increase of area under the curve. So by doing this, what will happen is it will increase the heat rejection and increase the overall network. Okay, but there are other issues. So if you look over here at point 2, which is quite critical, condenser usually operates below 1 atm. Okay, so below than 1 atmospheric pressure. So when we lower the condenser pressure to 4 prime, the new location, so it will increase the likelihood that air will intrude, because the pressure from the outside will basically push inside and increase the erosion by impact of moisture droplets on the turbine blades. Okay, this is critical. Okay, if you look over here, yes, if we move from 4 to 4 prime, what will happen is we have this an increase of area under the curve. Okay, that's what we wanted. So we get an increase of W net. But if you look at the position of point 4, 4 is very, very close to the saturated vapor line. So let's say your the quality value is roughly, let's say 0.9. Now, when you lower the pressure, means that you push down the line up into 4 prime, you see that your new location, the exit of the turbine, is now going further away from the saturated vapor line. So your X value here must be obviously must be very, very low compared to, let's say this is X1 compared to X1. So when that happens, again, remember this is all saturated mixture region. So as you have more vapor, more liquid in your system or at the exit of your system, you will increase the likelihood, or you will increase the probability of the moisture droplets to affect the turbine blades, okay? Wear and erosion. Okay? So that's the main issue. If you lower the pressure, yes, you'll get an increase in area under the curve, but the consequences of that means that you need to think about the erosion or the wear and tear of the blades due to the moisture. Okay, so it's highlighted over here, the increase of moisture content. So that's the critical issue. Okay. All right. The second thing that we can do, okay, to help increase the area under the curve is over here by superheating the steam to high temperature. So 3 is the original turbine exit, turbine inlet. Now, to increase area under the curve, remember, this is area under the curve. We can push it to the right, basically by superheating the steam to a higher temperature, Okay? Okay. So this pretty much can solve the problem that we had before. If before we had higher moisture content at 0.4, by increasing the temperature, basically you move from 4 to 4 prime, you reduce the moisture content, hence you'll get less moisture coming out from the blades or coming out from the turbine. Okay. So this heat steams to higher temperature to increase T higher average and also reduce the moisture, so which is what we want. However, the maximum temperature is limited by thermal tolerance of the metal. It looks good on paper, but remember, everything is limited by something. You have a constraint. Okay, how much temperature can the turbine withstand, basically? Turbine blades, turbine blade withstand. Okay. Even if we can remove all the droplets, but if the turbine cannot withstand the high temperature, so it's useless. So it's limited by the tolerance of the metals. Okay. And stated here, right now, it's about 620. I think it has been an improvement over the years, slightly, but about this range, 6, 7, maybe 800 Celsius. Okay. And to solve this issue, again, reheating may be added to prevent falling into the saturated liquid vapor mixture region where turbine blade damage from droplets may occur. So basically, to avoid this, we can use also reheating, which we are going to look in a bit. Okay. So we look two things. First, we lower the pressure of the condenser. Second, we increase the temperature, basically into superheating the steam, okay, to a higher temperature. And the third point that we can do is to increase the boiler pressure. Okay. So again, if you look over here, this is original, and this is improved. And again, the target is to increase the area under the curve so that we get increase of W net. Okay. So to do this, okay, again, this looks good for one point, but on the other point, you see that at 4 prime or the new location, you basically increase the moisture content because of the location of 4 prime. Okay. And however, this side effect can be corrected by reheating the steam, which we're going to look in a bit. So there's no one thing that can be said, oh, this is the best method, this is not the best method. You do something, what you are trying to achieve, and then you look at the side effect and try to give the solution to the problem that you encounter. Okay. So we look at 3 main modifications or 3 main things that can be done. In general, it's all about increasing the area under the curve. First one, lower the P of the condenser. Second one, superheating the steam to a higher temperature. And the third one is to increase the boiler pressure. Okay. All right. Let's look at one example over here. This is regarding to the increase of the boiler pressure, okay, from 3 to 3 prime. So from here, we know that, not temperature, okay, temperature 3 prime is higher than temperature of 3, the original. And temperature is corresponding to the pressure. So P3 prime is also correspond to a higher pressure of the original one, 3. Okay. So if you look over here, okay, we can use this particular method basically by using reheating. Okay. So reheating in the turbine stage. If we add 1 or more reheating stage, okay, basically we can reheat the one that is coming out from the first turbine, and then we enter it again for the second turbine, so that we can reduce the possibility of the moisture content. Okay, so let's have a look. Why one is called HP and LP? Remember, HP refers to high pressure turbine. LP is low pressure turbine. Okay, why is it called LP? Okay, if you look over here on the diagram, if I can just go again. If you look at the diagram, okay, this is the 3 prime, sorry, 3 prime. Okay. So what happened is that after it exits the 3 prime, okay, it goes down, okay, basically goes out, and then it's being reheated over here Because it goes down, now the line is already different. Okay, remember for TS diagram, the lines correspond to different pressure. So now it increased again to the desired temperature. So over here, yes. Okay, sorry, I put back here. It's not higher, which should be the same. So we want our T3 prime to be equals to T3. Okay? So the temperature, that's the temperature that we want. But in terms of the pressure, because you already remove some of the heat and then you reheat again going up, so now we have a different line, line 1, line 2. So the first one is high pressure turbine, okay, because it is at a higher lines. Now the second one is at a low pressure turbine, but still the temperature output is the same. So that's why they call one is high pressure turbine, the other one is low pressure turbine, because of the location on the lines. Okay. All right. But nowadays, okay, to avoid passing through the mixture region, okay, they now basically, most of the power plants, they operate supercritically. Okay, what it means is that the P and T, it exceeds the critical point of the working field. So if you remember, the critical point is located in the middle here, where you got 50% liquid, 50% vapor. Okay, instead of passing this point, basically, it goes, instead of going through this point, it goes straight past the point, straight into superheated region. Okay, so that's, they call it supercritical Rankine cycles, and it's being used by most of the industries. So for example, so this is a Rankine cycle for a real working plant, Sasan UMPP in India, if I'm not mistaken. Yes, project in India. Okay, so this is the diagram given by this particular author. You can see that over here, the diagram shows two turbine expansion. Okay, stage 2 to 3 and 4 to 5, and the reheating happens between 3 to 4. So this, if I can label this, is the reheating. So you can see that T2 is almost the same as T4, okay, which is, this is turbine 1, turbine 2, which is low, high pressure turbine, and this is low pressure turbine. Okay. So this is being used in the real Rankine cycle in the industry, and you can see that it bypass the dome. Okay, basically it's supercritical Rankine cycle. Okay, it goes past the critical point up into the turbine. So in this context, it is supercritical and it utilizes the reheating process. Okay, so reheating, high pressure turbines, okay, goes down and then go back to almost the same temperature. But right now, because this is line 1, line 2, line 1 is higher than line 2, so we get P2 higher than P1. Or is it P1? Sorry, P1. P1 is higher than P2. Okay, so that's about something about reheating, okay, and supercritical. Okay, so I think that's all I have for today's lesson. I will provide the asynchronous material for Monday's course, for Monday's session. So please watch that video, and hopefully for the next Friday session, we will finish Rankine cycle. Hopefully the video should finish everything by Monday. And for the next Friday's lecture, please bring some questions. You can do the tutorial. Basically, we'll pretty much will be tutorial based session. Okay, we'll look at before I let you all go, just a friendly reminder, I've set a special session for special replacement quiz for several students who were not able to attend the quiz last week. So please make sure you know who you are. Those who have those who have contacted me, I've informed them. And then other than that, that's it. So if you got any questions, please let me know. Otherwise, thank you everyone. Have a good weekend. Assalamualaikum. Very good. Assalamualaikum. Very good.
Thank you, sir. Thank you, sir.
Thank you, Doctor.
Thank you, sir.
Thank you, Doctor.
Thank you, sir.